Hello, everyone. I am Nafise Sedighi, a PhD student at Instituto de Astrofísica de Canarias, under supervision of Eduardo, Mark, and Isabel, and also a part of the Substellar group in the IAC. So today I'm going to talk about a bit model and comparing with the Euclid data. This is the overview of the project. At first, we are going to make a model, and then we are able to compare to the data. As you can see, for the models, we need to set some of the parameters and then generate the atmospheric model and produce the spectra at the end, then compare to the Euclid data with chi-square fitting method and having the best fit parameters. So first, I'm started with the models. So we need to have a grid setup and produce the pressure temperature structure. So we need at first choose our chemistry. That by chemistry in the ATMO model, we have the equilibrium and non-equilibrium one. And under this assumption of the chemistry, we are able to calculate the molecular abundances. As you can see here, for example, in this plot, the solid line is the chemical equilibrium, and the non-equilibrium one is the dash ones. So I show you some of the atomics and molecular that we have in the ATMO here. So the next thing that we need to set up is the opacity files. Opacity files includes the line list file that they are include the atomic and molecular line transitions. So that we used the line list database that provided by High Temp or ExoMol. And also we another things that we calculate is broadening, the Doppler and pressure broadening in the opacities files. And if you want to take a look at this website, this is the useful website that you can see the opacity files and play with the temperature and pressure and see how it's changing. So another thing is the fluxes. The fluxes that we have in the ATMO is the radiative flux and convection flux that we actually solve the Stefan-Boltzmann equation. And we have this equilibrium that the sum of the convective and radiative flux is the internal heat flux of the models in the atmosphere. Then we will, the code is repeating this process, solving all these steps and to converge the best pressure temperature models. And then when we have the pressure temperature profile in the several layers of the atmosphere, we will produce the spectra. So this is in the ATMO 2020 models, we have the equilibrium and non-equilibrium chemistry. Effective temperature is from 200 to 3000 Kelvin. Gravity is from 2.5 to 5.5, and the solar metallicity. In the new version, we have done the converge more models with non-solar metallicities. As you can see here, from 0.5 to minus 1.5. And also, we are having more updated opacities. Until now, we have added MgO and SiO molecules, opacities. So these grid of the models, they are, then when we have those pressure temperature, we will have the synthetic spectra that you can see in this plot, how the spectra is changing based on the different metallicity and how the absorption of the molecules is different per bands. And this is the Euclid range that I am working on for comparing the data. So now we have the models and synthetic spectra. Is the time to compare to the Euclid data. So the The Euclid data is good because the resolution is 450, and the wave length is 1.2 to 1.9 micrometer. So this is useful for us to study these substellar objects. I'm not going to explain more because we have an entire session about the Euclid today. So the sample that I used is all the identified objects that Carlos Dominguez, another member in our group, identified by the spectroscopy. And we have at least 15 T dwarfs and all the type from the M6 to T. And I use those spectra and comparing with this. That is in this plot, you can see the histogram of all these samples that we have all the spectral type more or less for to compare. And the Euclid is also, we are hoping to detect more fainter and cooler objects like white dwarfs by Euclid DR1. So, okay. Yeah, and the number of the object is 178 object. In this plot, the black one is the Euclid, and the rest is the ATMO 2020 and ATMO new version. So as you can see, the fit is really good. Actually, with this T7 that you can see here, and I used here the chi-square fitting method, and you can see if we take a look in residual and uncertainties, you can see this is the best fit of the models that we have the residual between 0.04 and minus 0.04. So, and then we will have the effective temperature and gravity and metallicity of the best model. So as I put another example for you is T6, and this is the Euclid observed spectra has a bit noise, so this is effect on the fitting, but we are hoping to have more better. Sorry, I need water. So in this object, as you can see, the residual is more because the Euclid also, it wasn't in the best quality in this, and so this is one of our challenges. But hopefully with the Euclid DR1, we will have the more and better observed spectra. So we did this comparison for all of the samples, and you can see here how the temperature is changing from the M type to T type. And it shows us that ATMO, it works well for predicting the effective temperature of all the T type. But when we goes to the L type, we see the offset, and for the M type, a little bit offset. So for the L type, we still needs to invest more time and maybe compare with the other models because still in the ATMO, we don't have the cloud and dust. So we are thinking to update the models in this scenario also to include them. But still, we are not sure that is because of the lack of the observed spectra that we had, or is because of the models. But we have to investigate more time on that. And the metallicity, as you can see here, is the metallicity versus the spectral type. And the metallicity is more or less the solar, and it makes sense because the sample, it was the solar metallicity more. And then the most common one is the solar one, but is spread in all of the range of the metallicity. For the gravity, you can see here For the gravity also, we have the spread plot, all the objects with all the gravity values, but for the T dwarfs that we obtain the gravity for, we can say that these are might have the planetary mass object, and based on these two references that I put here for you, the figure 4 of the first one and the figure 15 of the second one, it shows that the evolutionary models based on the evolutionary models in these two reference, they showed these objects with the gravity below 4 and 4, they have the planetary mass object. So hopefully with the new spectra, we will have more results based on these T dwarfs. So future steps for this work is that the working on the different metallicity, and maybe because now the steps is 0.5, so we are thinking to have the smaller steps for the grids, and also updating the opacity, adding the more opacity files in the ATMO, and converging the models for non-equilibrium one, different CO ratio type, and at the end we will use these whole grids of the atmosphere model to produce the evolutionary models. So this is the take-home messages that I can say that Euclid is worked well for the substellar identifying substellar objects, and the ATMO is predicting well the T dwarf effective temperature, gravity, and metallicity. And the solar metallicity, it was common in our sample. Then hopefully with the Euclid and ATMO, we will have the good result on studying these substellar objects. Thank you, all of you. And this is we are organizing another substellar conference, and you can see the website, and the registration is open, and hopefully see you next year. Thank you.
You forgot to mention the eclipse part of that. Question down here.
So how do you choose your temperature pressure profile and you don't have clouds yet in your modeling? So these are the two questions.
In the ATMO, we have the rain out and convective region. So it's kind of having and not having the clouds, because we consider that, okay, these molecules, they have the rain out, they change in the atmosphere. The position is important, and we consider that. But we don't have still that cloud and dust that, for example, the Sonora and BT Satel model has. So we are thinking that after this step, that we are working on the evolutionary, because if in the literature also we don't have any models for the lower metallicity, but so then we focus now in the lower metallicity. Then the next step is adding the clouds to the model states.
Other questions? Ethan over here. Oh, Ethan's up. We're going to Ethan, and then Matthew will go next.
Okay. Thanks for the talk. So what is the resolution of the newest ATMO models? And also, I want to check my interpretation of a slide earlier that for L types, it's over predicting temperatures by hundreds of Kelvin.
Yes, for the L type, we cannot trust ATMO in this level, because we have the offset, a lot of offset, and because we know also the L type has a dust and kind of strange atmosphere. So we have this offset in the, because as I saw in the other papers, we have still this unknown that, okay, why we have this offset with the models observed and the spectra in the Sonora, and also LOSI models, they have this. So still, we are not sure that is because of the dust, is because of the cloud, is because of what. So still we need to really study that part at L type L-type dwarfs.
So is this also true of the other models out there, like Sonora and BT Settle, that they're over predicting L temperatures?
I can say, yes, it's different. It's different offset, but yes, we have this in all of them.
No one of the models can fit the Ls, just to help you out. But none of the atmospheric models can fit the Ls.
BT Settle, for example, has dust, but Sonora has cloud. But still, I think we need the models to have both at least, and then say that, okay, it's because of the cloud. Yeah.
Last question, Matthew.
Very nice talk. You showed some of the T-dwarfs you found with Euclid. Are those representative of most of the T-dwarf spectra you're getting with Euclid, or are these the best examples?
These are the T-dwarfs that we classified by a spectroscope. Yes, we have more for sure by photometry, as Marusa's paper, in the Marusa's paper. But these are the objects that we identified that, okay, the spectra is nice, and we classify by the spectra. And if you want more information, you can go to the Carlos paper.
Do you have a lot of those T-dwarfs with well-fitting models with your Euclid data?
Compared to the L-type and M-type, not a lot, but yes, more than this type in this issue that I showed you.
Thank you.
It's still early days, right? You guys are still getting data, so there might be much more to come.
Yes. With DR1 data, yes, we supposed to have more, and because this cover more area of the sky, so we will have more.